Okay, so it's a pleasure to welcome all of you who are listening to this particular broadcast of the Wednesday Colloquium. And it's a pleasure for me to have one of our own, Professor T.P. Singh, give the colloquium today. So before I actually go and sort of introduce the topic and Professor Singh, let me just sort of give a brief introduction to the Wednesday Colloquium for those who are listening to us for the first time. The Wednesday Colloquium Forum is one of the oldest forum of science dissemination in the Institute. It was started under the stewardship of Professor Homi Bhabha, the first director, who really conceived this idea that all scientists, irrespective of not the caste creed, but irrespective of the scientific background, physics, chemistry, biology, should all get together once a week. And that date was chosen to be Wednesday at 4 p.m. To listen to very, lively expositions by experts discussing issues in contemporary science. So this has been sort of the heritage that has been passed on to me from generations before me, and people who have managed this colloquium series have really ensured that the crux that we have a broad audience and people try to disseminate ideas to a broader class of community, scientific community, is held through and through. So I'm really honored to continue this. Today we have Professor T.P. Singh, who comes to us from the Department of Astronomy and Astrophysics within us at TIFR Mumbai. And he is going to talk about towards the unification of the four fundamental forces, the current status of the Acheon theory. I just wanted to say that Professor Singh has been a senior member of the community, and he actually sort of has strong interest in laying down quantum foundations to different kinds of physical theories. And this is his sort of trial to make the unification come for all fundamental forces. And he's been a big proponent of this idea. So TP, thank you for giving this colloquium and you're sharing your latest ideas. You can start.
Yeah. Thank you, Jyotishman, for this very kind introduction. I'm audible properly?
Absolutely.
Yeah, so this is okay, yeah?
Yes, absolutely. Perfectly audible.
Okay, so these are the two highlights of my talk. Evidence that the weak interaction is the small distance limit of gravitation if the universe is 8-dimensional. And secondly, first principle theoretical derivation of the limiting low energy value of the fine structure constant given by this expression, which approximately comes out to this and agrees with the measured value to the 7th decimal place. So these are the two main things I will get to. This work is based on a few recent papers that I have listed here. Okay, before I go into the technical details, I would like to give you the big picture. So what I did, I made a 15 minutes long pre-recording just to keep the flow. I'm going to play that recording, it's an elementary overview of what I'm going to talk about. Just a summary. And after the 15-minute pre-recording, which I play now, I'll come back to the regular lecture and I'll talk to you. So we start. What is the Acheon theory? A candidate theory for unification of the four fundamental forces, which starts by asking how to solve the problem of time in quantum theory. What is the problem of time in quantum theory? Time is a classical concept. It's part of a classical space-time geometry, which is produced by classical bodies. These classical bodies are in turn a limiting case of quantum systems. There hence must exist a way to describe quantum systems without classical time, because we do not want quantum theory to depend on its own limit, namely classical limit, because these classical bodies are a limiting case of quantum theory. They are responsible for giving rise to space-time, classical space-time. And classical space-time is again being used to describe quantum systems. So that's a circular dependence which we would like to eliminate and hence find a way of describing quantum theory without using classical time. How to have a quantum theory without classical time? We will use Adler's theory of trace dynamics. So what is trace dynamics? Starting from classical dynamics, raise all position and momentum variables to matrices. These matrices do not commute. Now one could say, of course, that's what we do when we quantize a classical theory. We raise all position and momenta to the status of matrices or equivalently operators. These do not commute with each other. But in quantum theory, we demand that the Q's and P's, after being raised to operators, satisfy the so-called quantum commutation relations. QP commutator equals IH bar. However, in trace dynamics, we will not demand that quantum commutation relations be imposed. The matrices do not commute, the Q's and P's do not commute. The commutation relations are arbitrary. They are determined by the laws of motion. And the laws of motion are still those of classical dynamics. You can take the classical Hamilton's or Euler-Lagrange equations of motion, just replace the configuration variables and momenta by matrices. You will get Adler's trace dynamics. But if it was just that, it would be not very interesting. There's a twist. In what fundamental way is matrix trace dynamics different from classical dynamics? Well, there is a twist. The theory, the new theory, the trace dynamics or matrix dynamics, has a conserved quantity which is not present in ordinary classical dynamics. The following sum does not change with time. Take the commutator of Q and P for the ith particle and sum it over all the degrees of freedom. This is a conserved quantity. Now you notice in quantum theory, each of these commutators would have been independently conserved. That is not the case in trace dynamics. Each commutator by itself is changing with time, but the sum of these commutators is a constant. Each commutator, as you can see, has dimensions of action. It is as if the interacting degrees of freedom are exchanging action with each other, but the total action does not change. This is the principal difference between ordinary classical dynamics and its matrix version, the trace dynamics. In trace dynamics, the theory is assumed to hold at the Planck scale. It is a pre-quantum theory. Quantum theory emerges from trace dynamics at lower energies as a consequence of coarse graining of the underlying theory. What happens is that, I'm sorry, I have done some what is the icon? What? What is the icon? It does not change. This is the principal difference between ordinary classical dynamics is from trace dynamics at lower energies as a consequence of coarse graining of the underlying theory. What happens is then this conserved charge gets equipartitioned between all degrees of freedom, and each of the commutators then becomes a constant by itself. Sum is a constant, and after the emergence of quantum theory, each commutator by itself becomes a constant, and we set that constant equals IH bar, because it's same for all degrees of freedom. So in that sense, quantum commutation relations emerge from the underlying trace dynamics. In the underlying theory, there's no Planck's constant. There's no H bar. H bar is emergent at lower energies, and in fact, quantum theory is an emergent phenomenon. It's an emergent thermodynamic phenomenon. The underlying theory, trace dynamics, is deterministic, but Quantum theory is emergent along with its deterministic and indeterministic limits. It's emergent from the underlying matrix dynamics as a thermodynamic approximation. Okay, so as we said, trace dynamics is a pre-quantum theory, but space-time is flat in this theory. There's no gravity. At the Planck scale, the theory is assumed to have a flat space-time and no gravity. To achieve our goal of quantum theory without classical time, we will now raise space-time points also to the status of matrices. In trace dynamics, the configuration variables and momenta of particles and fields were raised to matrices, but space-time was kept as classical point structure. To arrive at our goal of quantum theory without classical time, we now raise space-time points also to the status of matrices, and we arrive at a generalized trace dynamics, which we can call pre-quantum pre-space-time. Trace dynamics, Adler's trace dynamics is pre-quantum, but it is still having space-time. Our generalized trace dynamics is pre-quantum and pre-space-time. So we have no longer any classical space-time, but the beauty is that there emerges a new absolute time, which we have called Cohn's time. It's a property of such non-commuting geometries in which space-time points are made into matrices that they have an inbuilt fundamental notion of an absolute time. So you lose classical space-time, but a new absolute time emerges, and which allows you to define dynamics. So that we are lucky. So we lost classical space-time, but we recovered a new absolute time. From here, so this is what we wanted. From here, there emerges quantum theory without classical space-time. It's also a quantum theory of gravity, which is called spontaneous quantum gravity. So in a nutshell, we took Adler's idea of a pre-quantum dynamics from which quantum theory is emerging. We generalized it to a pre-quantum pre-space-time dynamics by raising space-time points to matrices so that quantum theory emerges from here, but not just that, space-time also emerges in a different approximation. When many quantum particles get entangled with each other, a phenomenon called spontaneous localization occurs, and the entangled quantum system becomes classical. Concurrently, classical space-time emerges. Those quantum systems which are not too entangled remain quantum. So, at lower energies, from the pre-quantum, pre-space-time theory, at lower energies, there emerges quantum theory. But if there is a very large scale entanglement amongst these quantum systems, spontaneous localization occurs, the entangled systems become, quantum system becomes classical, and classical space-time emerges along with the emerging classical bodies. And those quantum systems which are not too highly entangled, they remain quantum. So this is the picture. We have now description of quantum theory without classical time that I just described is generalized trace dynamics and emergent spontaneous quantum gravity in Cohn's time. And from there, because of spontaneous localization, we can also have classical space-time geometry in mind. This leads us on to a new candidate theory for unification. So far, we only have quantum matter and quantum space-time in our theory, fermions and space-time geometry equivalently gravity. It turns out that if you would like to understand quantum spin in this pre-quantum, pre-space-time theory, we must introduce the other forces of nature, strong, weak, and electromagnetism. Remember, there is no Planck's constant, no h bar in this pre-quantum, pre-space-time theory, but we would like to understand how to define spin because quantized spin must emerge from here. So to define spin properly in generalized trace dynamics, we are compelled to introduce the other forces of nature. And not just that, we are compelled to double the space-time dimensions from 4 to 8. We are forced to introduce 4 internal symmetry directions because we want to understand spin. Spin is the rotation from space-time to the 4 new internal directions. Introducing ions and octonions. Just as space-time coordinates are real numbers, the coordinates in the new non-commuting 8-dimensional space are the octonions. So spin forces us to double space-time dimensions to 8. The coordinates in that non-commuting 8-dimensional space are octonions. An octonion is an 8-dimensional number with 1 real and 7 imaginary components. A real number is just that, it's a real number. A complex number has 2 real number components, a real and an imaginary direction. A quaternion has 1 real and 3 imaginary directions. And the octonion has 1 real and 7 imaginary components. These are the only 4 kinds of numbers in which the operations of addition, subtraction, multiplication, and division are possible. Complex numbers, real numbers, quaternions, and octonions are the only 4 possible so-called division algebras in which these 4 operations can be performed. So the octonionic coordinate system provides the space, the coordinates for these 8-dimensional physical space. An ion is the elementary particle in this space along with all its fields. So if we consider an electron in 8 dimensions, along with its gravity, its electromagnetism, its weak force, that is an ion. Similarly, a quark is an ion if you include, along with the particle, all the fields that it produces. The ion evolves in this 8-dimensional octonionic space in constant. So what's the picture? There's an 8-dimensional space whose coordinates are octonions. The elementary particles and fields living in this space are called ions. An ion is manifest all the aspects, the field aspect as well as the particle aspect. It's a bosonic plus fermionic. It has both aspects. And in this 8-dimensional space, it is revolving in constant. A candidate theory of unification. Octonions are non-commuting numbers. They very strongly constrain properties of allowed particles and fields. The octonions dictate that there are 4 kinds of forces, all unified at the Planck scale, that there are 6 quarks and 2 leptons for every fermion generation, and that there are 3 fermion generations. Because the elementary particles, the ions, are now living in this 8D octonion space, they cannot have arbitrary properties. The space, the algebra of the non-commuting space determines that there are 8 kinds of fermions. 6 of them are quarks, 2 are leptons for every fermion generation, and the algebra dictates that there must be 3 fermion generations and no more. And charge gets quantized. The property of the octonion that only quantized charge 1/3, 2/3, and 3/3 is possible. The octonions also dictate that 4-dimensional classical space-time emerges from the 8-dimensional space after spontaneous localization. Quantum systems which do not undergo localization live in the 8 dimensions. The Higgs mechanism and particle masses in the ion theory remain to be worked out. We have arrived at this theory of unification by addressing the time problem in quantum theory. So there's a deep connection between quantum foundational questions and the ultimate unified theory. Thank you for listening.
TP?
Yeah,
Yeah,
I'm
there are.
here. Now it should let.
Yeah, there are
Sorry?
some. There is a question by Unni, and I'm sure people will have some question But let me
This
frame Unni's question here. How are fermions defined, TP, without a notion
how
of
are without a notion of
how are fermions defined? With is it without a notion of spin? That's what
no
Unni.
no 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 I will build that now. The spin will be there, and there's also a definition in terms of Grassmann numbers. I do that. Can I go on?
Uh, Amol here, I just have one quick
Amol has a
clarification. Yeah. So
Yeah.
just to clarify the language. So you said once space-time raised to matrices, and at
Yeah.
some point you said space-time points raised to matrices. Are these the same concept,
Yes,
or are they
yes,
different?
yes. Space-time points raised to matrices is a more correct statement.
Okay.
Yeah.
Okay.
I will show you how that done. Please go on. Yes.
Okay. No, that's all. I wanted to clarify this statement.
Okay, thank you. Yeah, we'll see that now. So I wanted to give that overview because now in parts I will get somewhat technical because I also want to give you a flavor of the mathematics. So let's go on. So this part we have seen that we want a description, a formulation of quantum field theory, which does not depend on classical time. We are already reasoned this. Okay, and how do we want to do it? Stephen Adler gave matrix dynamics, which is a pre-quantum theory. In his theory, space-time he kept flat. So that is an approximation. So then the later part I have added how to include gravity, quantum gravity in Adler's theory. So once more, a quick crash run through Adler's trace dynamics. So here's an example of Adler Lagrangian. Suppose you had a classical C number variable Q and a Lagrangian Q dot square minus Q square, say a harmonic oscillator. What do I do now? I raise Q to the status of a matrix, equivalently operator. Let's say Q hat. So this is now a matrix polynomial. Q hat square minus Q hat dot square minus Q hat square. I take the trace of that. I do a time integral. That's my Lagrangian. So this is the kind of matrix dynamics we are going to do. Uh, our Qs will be what are called Grassmann number valued matrices because we need to describe bosonic and fermionic degrees of freedom both. So I come back to it. This is an example of an Adler trace dynamics Lagrangian. There's a scheme, there's a procedure of how to vary this action with respect to matrices so that you'll actually get a equation of motion which is where were we? Yeah, which an equation of motion which is q hat double dot equals minus q. So you get a classical mechanics equation of motion, but these are now matrices. So this is going to be our pre-quantum theory. We are not going to quantize it. We'll see how quantum theory and the classical limit emerge from this pre-quantum theory. Like I said, it is not a trivial extension. If you just put matrices and you still have classical dynamics as Newton's dynamics, not very interesting. But it so happens that because we are now dealing with matrices, the theory has an additional conserved charge, which is not there in classical dynamics. Overall, okay, I should define now what are bosonic and fermionic degrees of freedom. These matrices are made up of Grassmann number elements, which, as you know, anti-commute with each other. So QF is made up of Grassmann number elements. So these are called fermionic matrices. On the other hand, bosonic matrices are made up of even grade Grassmann elements, where if you have multiplied two Grassmann elements together, then they will commute amongst themselves. Even graders all commute with each other. So those we call bosonic. In QFT, in quantum field theory, we use bosonic matrices to describe bosonic fields and fermionic matrices to define fermionic fields. So to answer Unni's question, this is the definition of a fermion. A fermion is a dynamical degree of freedom, which is made up of odd grade Grassmann number matrices. These are even grade Grassmann number matrices. And any Grassmann matrix can be split into a bosonic part and a fermionic part. You can always do that. On the other hand, our icon will be actually something like a QB plus QF. So the icon does not come with just having a bosonic or a fermionic nature. It is both. And as we go along, we will also prove that these fellows have half integral spin as and when H bar, right now there's no H bar. In fact, this is important to note. This fellow is the replacement of H bar, you see. There's dimensions of action. And as I said, this is a conserved quantity, but they are extending action. So this is as if there's a H bar, n times H bar for the whole system. And in the emergent quantum theory at lower energies, there'll be an equipartitioning of this conserved charge, the Adler charge as it is called, and every commutator and anti-commutator by itself become IH bar. So this is some more I degrees BI, FI, so some more all the degrees of freedom, and you have this conserved charge, and that is what makes all the difference. This trace dynamics is assumed to hold at the Planck scale, and I don't go into the details. Quantum field theory emerges from here in the low energy approximation. So here is just a little more detail of what I already told you. Nothing new here. So let's go on. Here's my conserved chart. And now we start getting a little bit more specific about the action and about the trace Lagrange. So again, you see there's a trace. There's a bosonic matrix, a time derivative. I should mention that we can also do field theory, just that then you will have a space-time volume integrals, and these objects will be defined at every space-time point, these QBs and QF. So QB is a bosonic matrix, a fermionic matrix. Beta 1 and beta 2 are two constant Grassmann elements because we want to make the Lagrangian bosonic. And again, you can make variations and get equations of motion. Okay. All right. What have we done? In going from classical dynamics to trace dynamics, we have skipped quantum field theory. We have become more general because we didn't fix our quantum commutation relations. And we recover, if we want to recover classical limit also, we ask the following question. What is the emergent dynamics if we are not observing at Planck time scales? My time resolution is not Planck time, which is 10 to the minus 43 seconds, but much poorer. So I coarse grain over time using statistical mechanics, statistical thermodynamics, and keeping my Hamiltonian and the Adler-Miller charge, the C object, QP commutator. Keeping these conserved, I ask, what is the emergent average dynamics at energies below Planck scale? So this is the standard statistical thermodynamics that Adler applied. I still describe his work only. There are two limiting cases. If the underlying Hamiltonian has a negligible imaginary part, quantum commutation relations and Heisenberg equations of motion emerge. So this is important. I will be working with the Hamiltonian, which is not necessarily self-adjoint. So that's very important and not disallowed because, at the Planck scale, I do not have a restriction that my Hamiltonian be self-adjoint. I should recover a real Hamiltonian at the energies where we do our experiments currently. So if the negligible imaginary part, the trace dynamics will give you quantum field theory, and you can construct quantum field theory from the emergent low energy theory. On the other hand, there's also a second limiting case. If the underlying trace Lagrangian and the trace Hamiltonian have a significant anti-self-adjoint imaginary part to the Hamiltonian, then what happens? The self-adjoint part of the trace Lagrangian collapses to the classical C number Lagrangian in a process called spontaneous localization. It's a kind of decoherence. So the trace Lagrangian goes to the ordinary Newtonian dynamics Lagrangian. It's like sending a matrix to one of its eigenvalues. So earlier we had raise C numbers to matrices. This is the reverse process. It sends matrices back to C numbers, provided there is sufficient so-called decoherence taking place. There's an anti-self-adjoint component is important. In fact, when does that happen? When does the imaginary part become important? It turns out that for a single degree of freedom, the imaginary part is very small. But if you have many, many of them entangled, the imaginary part becomes large and causes a breakdown of superposition and classicality is reserved. The quant is recovered. The quantum systems that we normally come across are not too heavily entangled. We have seen 100 degrees of freedom or maybe 1,000. A classical system is nothing but a hugely entangled quantum system, let's say around 10 to the 20 degrees of freedom, in which spontaneous localization has become very important. So the anti-self-adjoint part causes decoherence in the self-adjoint part, and we are back from matrices to C numbers. So in summary, from trace dynamics, you can get quantum field theory at lower energies for microscopic partially entangled system, and you can get classical dynamics at lower energies if the entanglement is very high, as is the case for macroscopic system. Okay, so this is Adler's trace dynamics. As I said, in this theory, space-time is flat, no gravity. To achieve our goal of quantum theory without classical time, we raise space-time points also to matrices, and we arrive at what I call a generalized trace dynamics, a pre-quantum, pre-space-time theory, which has a new notion of time, an absolute time, like Newton's absolute time. And we will repeat Adler's statistical thermodynamics, but now starting from a pre-quantum, pre-space-time theory. And how do we make this theory? Just as we, for matter and field degrees of freedom, we raised classical C number degrees of freedom to matrices, we have to devise a scheme to do that in a mathematically sensible way for space-time geometry. And there actually we employ Cohn's non-commutative geometry program. And in fact, there's a very nice parallel between trace dynamics and non-commutative geometry. You can think of trace dynamics as a map from the Hamiltonian dynamics in a phase space to a Lagrangian dynamics, then raised to matrices, that's trace dynamics. And again, you're back to a phase space matrix dynamics. What is done in Cohn's non-commutative geometry, you start with the ordinary geometry, let's say a Euclidean or a Riemannian geometry. You map it to an algebra, your algebraic spectral description of geometry. You make the algebra non-commutative. For example, if you had an algebra of space-time points, you will now make each space-time point a matrix. So the algebra has become non-commutative, and you ask, which is the kind of non-commutative geometry I have mapped it to. So what we are going to do in today's work is something like this. You know, you have a Euclidean coordinate system. I'm going to replace it by those 8-dimensional octonions, which do not commute. So that's the octonionic geometry is a good example of a non-commutative geometry, because the basic elements which are defining coordinates no longer commute. And in fact, there's an equivalent non-commutative geometry. So we have to work with the non-commutative geometry of the octonionic systems. This is a slightly heavy slide, but it's very important. This is the heart of the program. What did I do to raise classical general relativity to a matrix dynamics? What were my classical observables? In fact, they were not the metric. If a metric is already a matrix, I'm not going to raise that into another super matrix. Rather, we deploy something that Cohn's used very seriously, what's called the spectral action principle. So out here, this is the Einstein-Hilbert action. It turns out if you, on this classical space-time, Riemannian space-time, if you take the Dirac operator dB, the following theorem holds. The trace of the squared of the Dirac operator made dimensionless with Planck length In other words, it's the same as the sum of the eigenvalues of the Dirac operator squared. It's the same as the Einstein-Hilbert action. It's a beautiful theorem telling us that the eigenvalues of the Dirac operator capture information about the space-time geometry. It is these eigenvalues that I'm now going to use as classical C numbers, which are going to be raised to matrices. Which matrix? I raise each eigenvalue to the same Dirac operator of which it is the eigenvalue. So here is the map. So this is my classical Einstein-Hilbert action written in terms of these eigenvalues. I've just made a replacement, just done this. Now, each eigenvalue is raised to the Dirac operator. So this is the transformation from C numbers to matrices, and I define a gravitational dynamical variable QB, which is a matrix, whose time derivative, the so-called Cohn's time, I won't go into the maths of where this Cohn's time comes from. There's a new degree of freedom, fifth degree, a second time, you can call it, because I'm losing space-time. I'm making space-time points into matrices. I lost space-time, but I recover a new time called Cohn's time. And the Dirac operator to which this eigenvalue has been raised is used to give a definition of this dynamical variable QB. This is the definition of QB. In other words, when you go back to the classical limit by spontaneous localization, this QB, which is will collapse to an eigenvalue of the Dirac matrix. And since I did this for each eigenvalue, if all of them collapse, I will again have a set of eigenvalues whose square when summed will again give me the Einstein-Hilbert action. So this is an important principle to remember, how we went from classical space-time geometry to a matrix trace dynamics for gravity, and why that guarantees that in the classical limit we'll again recover general relativity. It is because of this connection. I can do something
TP?
similar for
Amol, I had a quick question. So since we don't know what is since we don't know right now what is Cohn's time, is it okay if we assume that right now to be just a parameter with which you are going to work, or is there some special property?
Yeah, we can do that. So throughout it will be like,
right now parameter is okay.
Yes, it's a time parameter which will help me with timekeeping. You're completely right. Yes, absolutely. Okay.
TP,
so what has happened?
TP, sorry,
just
another two questions on the chat. Konkar Ravi, I think he has, she has, I don't understand that, but has two questions.
Sir, can you hear me? I can ask the question.
Yes.
Oh, thank you.
Yeah, go ahead.
Hello, sir. I'm actually Shashidip sir's student. I'm looking.
Yeah, I know you. Yes.
Okay. So actually, I think the anti-Hermitian nature of the Hamiltonian, is it because that you also assume that you are modeling the quantum system as an open quantum system, where you take the environment?
No, it is actually, you see, when I write the Lagrangian, it is very naturally not self-adjoint. And I'll have to work very hard to remove the imaginary. But you'll see, it's already there in octonions also. 7 imaginary directions. When your coordinate space itself is quote unquote so imaginary, you should be prepared for a Hamiltonian which is not self-adjoint. I didn't put anything by hand. It's not an open system. In fact, it's a closed system.
No, I'm saying if you like this, the anti-unitary nature of the Hermitian itself, it seems to like incorporate the open, to incorporate the open.
No, that's what I'm saying. It's not so. As you see, you'll see as we go along what's going on. Yeah?
Okay. And the second one is the summation of the eigenfunctions of the spectrum from Cohn's theory. Is it like this zeta function with the S parameter being -2 because -half? Because that seems to match.
No. It is much more basic than that. No. There's no zeta function kind of regularization. It's very simple actually. It's a theorem in geometry.
Okay.
Okay, shall I go on? All right. So what
Okay.
has happened? I had this Einstein-Hilbert action written in terms of eigenvalues. Each eigenvalue itself has now become trace QB dot square integral over Constein. So this is this is like one icon. So earlier this would have been just one eigenvalue, but now it has become in itself trace QB dot square integral Constein. When spontaneous localization happens, this object will go back to one of the lambda i's. And so now for each eigenvalue, it's like having a full universe corresponding to each of the eigenvalues. And the total universe is the sum over I of all these ions. This is what I call an ion, an atom of space-time matter. The fermionic part has come from this matter action linear in mass. I don't have time to explain what I did here. So at the Planck scale, the total universe is made up of enormously many ions, as many ions as the eigenvalues of the Dirac operator. But we will work with only one of them. They are all copies of each other. What I will show to you is that this contains the standard model quarks and leptons, as well as the bosonic degrees of freedom. Once I write this in an 8-dimensional octonionic space, we actually sharply define that the fermions are actually quarks and leptons. This is dictated by the space. I don't have a freedom. So this is Cohn's justification for what I call Cohn's time. We skip that. Okay, and this I've already explained. If I have a pre-space-time, pre-quantum theory, the spontaneous localization caused by the imaginary part will give us the classical space-time, and those quantum systems which are not too entangled, they will remain quantum, and I can then do quantum theory for them on the emergent classical space-time. So what's happened? Part of the universe becomes classical, matter becomes classical space-time is recovered, but there are other quantum systems still not classical, the so-called ions, my electrons and neutrinos, they are quantum. I can write a quantum field theory for them on this classical background. There's just some advertisement for a meeting going on at Perimeter on octonions and the standard model. Okay, now we are going to change from a 4-dimensional to a 8-dimensional theory. I'll explain why we do that. So here's a quick introduction to what an octonion is. As I said, there are only 4 division algebras: real numbers, complex, the quaternions, and the octonions. These, as you're familiar, have 3 imaginary directions, each being a square root of -1. They anti-commute. Ij is k, jk is I, and you can, I think ki is j, can make the third one. So in this picture, the point 1 stands for the real line. So that the real line is here. And if you take this plus any of the 3 lines emanating from this point 1, you'll get the complex number. If you take any of the 3 planes emanating from 1, you'll get a quaternion. So these planes are quaternions. And this entire cube on which this E1 to E8, E1 to E7 are marked, this is the octonion. The universe that we live in is like one quaternionic plane, say 1, E6, E1, E5. That's our universe. It's very large in extent. What we are going to propose is that there are 4 so-called internal directions along which the other forces lie. The gravity lies in this quaternion. The other forces lie essentially in all the 8 directions. They are there in our part of the space-time also. These dimensions, therefore, reasons like for fine time go into, are very thin. They are not compactified, unlike in Kaluza-Klein string theory. They are not compactified. Their thickness is of the order of the quantum wavelength of the system that we are talking. So the thickness could vary. For some quantum system, this thickness will be very low. For some, it will be very large. Classical systems do not penetrate into these internal directions. Why? Because their Compton wavelength is much smaller than Planck length. The recent quantum classical systems don't penetrate. This is because the associated quantum length is too small. They stay on the 4-dimensional space-time. Whereas quantum systems, in our theory, quantum systems are by definition living in 8-dimensional space. The quantum properties arise as a consequence of their penetrating these other 4 non-commuting directions. And as we said, we will see that the fermions as well as the bosons in this space-time cannot have arbitrary properties. The space-time will dictate the properties of the particles. This is the multiplication rule for the octonions, don't need it. Okay, so this Lagrangian we have already seen. This is a purely gravity plus fermion Lagrangian. There's one free parameter only, the length scale associated with the ion. There's no mass, no charge yet. You see, there's no charge also right now. This QB is gravity, QF is the fermions. There are 3 fundamental constants: Planck time, Planck length, and this object has dimensions of action. This is basically the scalar made from the Adler chart. Eventually, this will become identified with Planck's constant. So one constant of action, one Planck time, and Planck. I will extend these for G, H bar, and C. I don't have a G Newton, that will emerge. I don't have a H bar. This will become H bar. And speed of light is defined as the ratio of Planck length to Planck time. So there's one nice thing you see, this action is entirely dimensionless. Everything is scaled. In fact, you can, you should be able to, this also can be, this is also in a sense already scaled because, this time derivative that is C tau, the Q's have dimensions of length. So QB dot is actually, QB dot and QF dot are actually dimensionless. So, okay, so this is a step in a sense towards number theory. Everything here is in a sense a number. All right. Now I want to ask how to include Young-Mills fields, which I have been saying are needed for understanding spin. We do the usual thing that we do, and we want to generalize the Dirac operator to have a potential. This is my Dirac with Heinz, keeping in mind that this actually was the Dirac operator. I add a potential-like term. This will actually describe the QCD and electromagnetism. This alpha is the important new constant introduced in the theory. In fact, the fine structure constant also comes from. This is not the fine structure constant. Sorry for the notation. But the fine structure constant will be a combination of alpha and L. It will be alpha square into L1 over L4. I'll actually prove now by the end of today's talk that that object is numerically 1 by 137. I did not put it in by hand. It will just come out from the algebra of the octonion. So similar generalization in the fermionic part. The second bracket also a potential is added. And by redefining this Q1 and Q2 variables, I can write this Lagrangian in this very nice and simple form. And it's actually describes, we'll see, once written in octonionic space, if you assume that this Grassmann matrices have 8 components, 1 component for each octonionic direction, so basically sum of 8 matrices, we will be able to argue that this actually describes the standard model. When we open it, it becomes actually very big. There are something like 256 terms, but this is a nice compact way of writing it. Okay, so this was the point about spin that now I will argue why it's necessary to double space-time to 8 dimensions. And why do we bother to define spin? Because this is a Lagrangian dynamics. Or angular momentum comes from the variation of the Lagrangian with respect to the canonical angular velocity. If you give me a theta dot, Del L by del theta dot is angular momentum. Normally we do that for orbital angular momentum. And in quantum theory, spin comes from representations of the Lorentz algebra. We don't have that here, you see. But we have a Lagrangian. If we have a Lagrangian, our pre-quantum theory is a Lagrangian dynamics. So I must have a way of defining spin, which should match with the conventional definition of spin in quantum field theory. Okay, so this is the same Lagrangian that I showed you. Here's an alpha. There are these L's written out in some, sorry, maybe it's confusing you. I make some redefinition. Just notice that this is very simple. This QB dot is like the real direction, and this is like this complex I square root of minus 1 is giving me an imaginary component to that. So think of it as a plane, okay, in which gravity, QB dot is gravity, that's along the real axis. The Yang-Mills field are along the imaginary axis. So I define a complex number in this sense. Think of this as a complex variable, for which I can do a polar coordinates, the magnitude, the radius, and the angle. This angle is in this plane. And now I can, as usual, define my linear momenta from the Lagrangian. And this bit is new. See, I can define orbital angular momentum also. But this bit, what I'm interested in is look at the way this angle has been defined. Let us look at this picture. So this is the real space-time direction, 4D space-time. Now I introduce 4 internal symmetry directions. Why 4? Because, if these are 4, then makes sense that these are also 4. Okay, so this is a cartoon of the plane. That spin is defined as a rotation from space-time to an internal direction. And I'll argue that this is actually related to the weak interaction. These 4 internal directions will be for the QCD and the electromagnetic interaction. They come here. The weak interaction sort of mediates between space-time, 4-dimensional space-time and internal direction. But strictly in this theory, the weak interaction is a part of space-time, not a internal symmetry. So I call that the Lorentz weak symmetry. That's another point to remember, that now there is no gravity. There is a spin 1 universal Lorentz interaction. I hope I can bring out that picture when we go into the octonions. That is described as these first 3 terms. Notice there's no alpha here. The coupling is dimension full. It is LP square, just as for gravity and for the weak interaction. The couplings have dimension. These 2 terms presumably describe Higgs. These 3 terms will describe, I try to justify, QCD. This will be 8 gluons, once written in the octonionic space. And this is the action of the gluons on quarks. And here's the coupling. This is the fundamental coupling constant in our theory, which will also be part of it in one combination. This will be the QCD coupling constant, and the fine structure constant will also be made from this. The QCD coupling constant at a specific energy will be related to the fine structure constant. They come in a certain ratio. Okay, so what have we done? We have moved on from a 4-dimensional space-time to an 8-dimensional space, and this is an assumption that that space is the space of octonions. 1 real direction is here, 3 non-commuting additional directions here, and 4 non-commuting octonionic directions here. The space has become non-commutative. Ordinary space-time will be recovered, the 4D space-time will be recovered from here through spontaneous localization. So the ion evolves in this 8D octonionic space in Cohn's time. Another nice thing that happens, earlier we had space-time diffeomorphisms along this spatial part. We had internal gauge transformations along these 4 directions. They are now all unified into what are called algebra automorphisms. maps from one set of octonionic coordinates to another. They are not coordinate transformations in the general relativistic sense. They are what we call algebra automorphisms, mapped from one octonion to another. So these 8-dimensional algebra automorphisms take the place of space-time diffeomorphisms and internal gauge transformations, together giving us this 8-dimensional space-time in which we now have a unified theory of the Lorentz interaction and the weak interaction and the internal symmetries. All that is dictated to us because we are now in an octonionic space. And so this is for one ion. It's as if this is the entire universe. And we'll have the same physics for every octonion. And when many octonions entangle, then you have spontaneous localization giving rise to classical emergence and gravity. For those ions which have become classical, they'll stay here. Quantum systems will continue to live in all the 8 directions. As I said, in our theory, quantum mechanics is by definition a 8-dimensional theory, which may look surprising. It's just that the thickness of these additional dimensions is of the order of Compton wavelength, and saying that when we do quantum mechanics unwittingly, we are actually probing these 4 other directions.
Sir,
Okay.
I have a small question. Can I ask?
Yeah.
Sir, you said that the spin is actually a rotation from 4D space to this 4D internal directions. Right? How do we differentiate whether it is half spin or integer spin, half integer spins or integer?
Good. Good point. You stopped me. I actually proved that when quantum, so at the pre-quantum theory level, it has no definite quantization. There's no H bar even, right? In the emergent trace dynamics, when H bar emerged, because of the equipartition of the Adler charge, I could prove that spin is a multiple of H bar, and it is a half integral multiple of H bar for the fermionic degrees of freedom, and an integral multiple of H bar for, no, actually strictly, I only get half H bar and H bar. H bar for bosons, half H bar for fermions. So it seems like this theory is saying that no higher spin fermions. Maybe I'm wrong on that. And there's no spin 0 either. So the picture right now, which remains to be understood better, is that the Higgs scalar is actually made from fermionic degrees of freedom and has a net effective spin 0. So in a sense, this is actually a proof of the spin statistics theorem, not from spin to statistic, but from statistics to spin. Already defined bosonic and fermionic degrees of freedom as those made from odd or even grade Grassmann matrices. Then I proved that the odd grade Grassmann matrices have half integer spin, half H bar, and the other one have H bar. So in a sense, this is the proof of the spins.
Okay. Thank you.
TP, please continue. Hello. Hello. TP? TP,
you are frozen.
TP, please continue. How only?
I think he is frozen. His line is cut.
Yeah, I'm actually, I think he's now going to try again. Reconnecting. I just would like all of you to be a little bit patient as he joins back. Yes, Sanjay, I'm calling. It's not picking up the phone.
Hello.
Into some other dimension.
Hi, TP. Hi, TP.
Somehow the electricity went in my house. So now I have to give me 2 minutes. I will have to connect my system, somehow bring it back online. You are on? I'm on my Geo data. Okay, so I have to get my talk here. So connect me to Geo data here. Please, I'm so sorry.
No, it's okay, TP. We are waiting. No problem. Please take your time.
Either in my house or in the residential campus, the electricity has gone.
Residential place, I think it has gone. Residential campus, the electricity has
You also don't have it?
No.
Okay. So I should be able to use Bluetooth and come online.
Oh, okay. Sorry about that.
No, it's okay. I should be sorry. Maybe if I had been in the institute, it would have been okay. The Bluetooth, is it?
Go to your meeting and say, you can take mine only. Check mine.
Yeah. So how do I find it?
Go to Wi-Fi.
Hello. I think we lost him again.
It's not easy. If there is no power, it will take some effort to connect back and put the talk on.
Yeah. Please, I would request all the audience to please hold on as he gets back.
I see that no theorist except Amol is around.
Amol is there. Yeah, Amol is there.
No, Shiraz is also
Ah, Shiraz is also there.
Oh boy, entire colony is out of electricity, it says.
Oh, the colony.
Yeah, much bigger problem.
Oh.
Oh boy. ये बंदा आने वाला है, क्या होगा मेरा वतन?
So the BEST has to come, I guess.
Go for tea.
Okay, TP is back. TP is back.
Oh,
Guys,
very good.
you need to unmute yourself. Unmute yourself, TP. You need to unmute. We can't hear you. Just go to the mic at the end of the Zoom and the left bottom part, unmute.
The slides are on.
Yeah, the slides are on. He just needs to unmute.
Okay, now is it
Yeah,
better?
perfect.
I'm so sorry, man.
No, it's not your fault. It's just the entire colony, it seems, has lost power.
Yeah, okay. So where were we? I think we were on this slide.
Right.
Can I go on now? Okay, can I continue?
Yes, please,
Yeah,
please.
so I was saying that the weak interaction mediates between space-time and the internal symmetry directions. QCD and electromagnetism is in there. Weak interaction is mediating, and there is a Lorentz weak symmetry which is dimensionful, which is described by the first three terms, and these three terms will describe QCD and electromagnetism. Okay, so let's go on. This I think I've already done. This is elementary. So this is the build up on the work of some people in the last few years, which have used quite heavily. Okay, now comes the central question. Where do the quarks and leptons show up? Do we know from the octonion that that's all that we can have as elementary particles? So, so get a little bit technical, that there's an analogy between what we do quaternions and what we do with complex octonions. So these are now complexified octonions, complexified quaternions. From these number systems, you can make something known as a Clifford algebra, which is very central in this discussion, from which you can make things spinors, also known in mathematics as minimal left ideals. In this left-hand side construction, you get the Lorentz algebra SL2C and left and right Wild spinors. You do exactly the same thing with complex octonions. You get a different Clifford algebra. This is CL2, this is CL6. It turns out that the corresponding thing to left and right Wild spinors here are an 8-dimensional state basis whose properties actually get determined from the Clifford algebra. In particular, you see that there is a quantum number, which is a U1 number operator, which is defined to be 1/3 of a thing we call charge. And then we show that because of this nature of this algebra, the charge only has values 0, 1/3, 2/3, and 1. Okay, so that's a hint. Then we also show that there is a SU3 symmetry because dictated by the octonion algebra. I'll come to that. There's a SU3 symmetry under which this 8-dimensional basis has a very specific property. There are two of these basis spinors which are singlets under SU3. And these two happen to be the ones which have charge 0 and 1. So that clearly tells us that, these SU3 singlets with charge 0 and 1 can be identified with the neutrino and the positron. And then there are three of those basis spinors transform as anti-triplets under SU3. They happen to have charge 1/3. So we can define them as anti-down quarks. And the remaining three are triplets under SU3. They have charge 2/3. And so we can identify them with the up series of quarks. And this is it. There is no more left apart from except that there is a conjugate 8-dimensional basis which gives us the 8 antiparticles. So that's the philosophy, that starting with complex octonions, you can make a Clifford algebra from which you get a spinor basis which has specific properties under SU3 and U1. Of course, we should ask so I'll come back to this. Where do those SU3 and U1 come from? I'll go back in a few minutes. This is the automorphism group G2 of the algebra, automorphism algebra of the octonions. It has 14 generators, which in fact will identify with 8 gluons, 1 photon, 9 and 3 weak isospin bosons, 12 and 2 newly introduced Lorentz bosons. So this G2 has a very interesting subgroup structure. It is the only subgroup structure you can have in G2. It has two maximal subgroups. One is U3, which is SU3 cross U1. The other is an SO4, which I can think of as a SU2 cross SU2. Now, if someone asks, where did these come from? Why not SU4? There's no SU4 inside G2, you see. These are the maximal subgroups of G2. They have, this fellow has 8 generators. This has 6 generators, 8 plus 6, 14. So it is as if the standard model along with the Lorentz symmetry is sort of presented to us on a platter when you look at G2. There's no guts here. I don't have to worry about SU5. Is it SU5 or is it SO10? The exceptional Lie group G2 and its higher versions F4 and E6, they provide us with this unique structure. So that is where, so firstly we will deal with SU3 cross U1. This is, and then we come back to this, which I identify with the Lorentz weak symmetry once we complexify this G2. Very interestingly, the weak interaction SU2 is sitting in the intersection of the SU3 cross U1, and this is the Lorentz weak symmetry, the space-time part in the 8 dimensions. This is the so-called matter content, the QCD, electromagnetism. This is where the charge and the color the electric charge gets determined. And the weak interaction is a mediator between the internal symmetries and space-time. So what we normally thought of as, 4-dimensional gravitation and then these internal symmetries, the picture is changing now. In this 8-dimensional octonionic space, there is 4-dimensional space-time, that is this made from complexified SO3. And this fellow, the weak interaction, also U1, are actually sitting in an intersection as if the weak interaction belongs to both the internal as well as space-time symmetries. Okay, so now I think since, how do we do with time, Jyotishman?
So it's actually pretty close to 5:15. That's my sort of point, I guess.
Can I take 15 minutes?
Okay, maybe can we try to think of wrapping up? Yeah, 15 minutes is okay.
Yeah, because I do want to get to the fine structure constant. Maybe I skip these details, and you please, if you do not mind, take my word for it that the octonionic algebra, because of this is maximal subgroups that I just showed you, dictates for us this set of 8 quarks and leptons, because it tells us the behavior under SU3 and under U1. The charge gets quantized and we get singlets and triplets under SU3. So we know that the neutrino and the positron do not have the strong interaction. Okay. So I'll speed up, Jyotishman, I'll speed up. And you can similarly show, it takes some amount of work with the Clifford algebras, that I can no longer think of the weak symmetry and the Lorentz symmetry separately. They come together in this group SU2 cross SU2. In the Clifford algebra CL6 language, we cannot separate them. So that is what I call the Lorentz weak symmetry. So what happens when there's electroweak symmetry breaking? We do have electroweak. So, the total symmetry is color, electro, weak Lorentz. When symmetry breaking happens, color electro separates from weak Lorentz, and the spontaneous localization process, which gives rise to the emergence of a classical space-time, brings the weak interaction along with it, except that the weak interaction is now the small distance quantum counterpart of the Lorentz interaction. And many ions along with their Lorentz interactions put together is what give rise to gravity. So gravity is there's no spin too. We won't quantize gravity. We're quantizing this so-called Lorentz spin-1 interaction. So there are 2 Lorentz spin-1 bosons which replace gravity and which interact universally, giving us a total of 14 spin-1 bosons, which are all massless before symmetry breaking. And so yeah, that's the story, that we don't quantize gravity. There's no spin to graviton in this theory. So you could call it a prediction that in the non-symmetry broken phase, there are these Lorentz bosons, and above the electroweak symmetry breaking scale, say around the TeV, we must look for these objects, spin 1 Lorentz bosons if this theory is correct. Okay, so I think I can move ahead. I have given you some flavor of how the octonionic theory, because of its maximal subgroup structure, gives rise to the fact that there can only be these kind of fermions and their antiparticles. There has always been in the literature a physical motivation for gravi-weak unification. We keep electro-weak, so it's always color electro-weak gravi. Weak interactions, we know, violate parity, which is a space-time and spin feature. The weak interaction knows about space-time and hence gravity. These GF, the weak coupling constant, is dimensionful, and so is G Newton. Whereas the alpha in our theory, which is the QCD and EM dimensionless coupling, these are dimensionless. So weak goes more naturally with gravity. And our Lagrangian, as I said, also strongly suggests gravi-weak unification. So does the subgroup structure of G2, and the Clifford algebra structure applied to the octonions very strongly suggests that you cannot separate weak and Lorentz. Okay, so the kind of symmetry breaking that will happen in our theory is something like, for example, we just studied this, and one example of such a paper, Gates' theory of the Lorentz group as a source of dynamical electroweak symmetry breaking. This is the kind of thing that we have in mind. Spontaneous localization, emergence of classical space-time is also the same process which causes the electroweak symmetry breaking. So this I have already gone through. This also we know. Okay, and now it turns out that this same Lagrangian can be easily generalized to address 3 generations. So far I was talking of only 1 generation. I should be done in about 5 minutes. So long, it turns out that there are certain total time derivative terms I dropped, but if I do not drop them, I get enough freedom to describe 3 fermion generations, and uh, we actually go to the next algebra known as sedenions, is a 16-dimensional counterpart of octonions, but we come back to octonions. Essentially, the sedenion algebra is 3 copies of the algebra of octonions. This is the permutation group S3, which is isomorphic to spin 8, if you know this language, which is related to SO8, which has a famous property called triality, which is basically saying you make 3 copies of SO8 or 3 copies of the octonion algebra. And that suggests to us that maybe we can understand this way why there are 3 fermion generations. It has to do with this triality of SO8 and how G2 is related to SO8 and spin 7. Basically, you make 3 intersecting copies of G2 once you have this generalized Lagrangian. And okay, and that is, I think, shown in this next diagram. This is the proposed unification of the 4 interactions in this 3-generation theory. The automorphism group of associated with these 3 copies of G2, or in particular spin 8. Spin 8 is a subgroup of F4, and it is easy to argue that when you have 3 copies of G2, you should be moving on to the next larger exceptional Lie group, which is F4. So 3 copies of SU3, and very interestingly, the Lorentz and the electroweak parts sit in intersection. That's understandable. The space-time symmetry part is somehow common to all 3, but the quark lepton content is separate for all 3. Of course, we immediately ask, are there 3 copies of gluons, 8 into 3? That's a tough question with a certain argument that I cannot go into. I could save the Lagrangian to be such that there are only 1 copy of the bosons, but 3 copy of the fermions. So now the last, and I think the most interesting part of the talk, how does the fine structure constant come? Okay, so it's a Lagrangian once again written in the simplest possible form, expanded out. And now I show you the 3-generation Lagrangian. It has these parts. The Lagrangian for the 14 bosons. Set 1 is for the Lorentz-weak interaction of the leptons. So these QBs here are describing the Lorentz-weak part, so to gravity and weak interaction acting on the charged leptons. So this is really one coupling. This L, and these 4 L's are now going to start differing from each other. They'll acquire specific numerical values. Set 2, the most interesting one, is the electromagnetic interaction. And this is our fine structure constant. Alpha square LP4 over L4. The LP can be made 4 and divide out. So alpha square LP4 by L4 is a fine structure constant. And this has to do with the QC decoupling constant that I will not talk to. But you see the alpha, the one and the only fundamental constant that we had in our theory, the alpha, is now entering along with this L to define the fine structure constant. And I'm going to find out again from the octonion algebra a value, numerical value for this object. Okay, when we are dealing with 3 generations of fermions, they are as if living on 3 copies of the octonion space. So I no longer have G2. I have something called like a 3 copies of G2. So one pair of, so the 3 copies of the 3 generations have associated octonions with them, and between them they are described by what are known as these so-called Jordan matrices of the exceptional Jordan algebra. Just remember that we are dealing with the automorphism group F4, which is also the automorphism group of these matrices. Suppose you made transformations on these octonions, x1, x1 star. Star is the octonionic conjugate. So x1, x1 star, x2, x2 star, x3, x3 star. Xi1, xi2, and xi3 are real numbers. So this I call a Jordan matrix. And if I have 3 neutrinos, I'll make a Jordan matrix for the 3 neutrinos, a Jordan matrix for the 3 charged leptons. Each lepton has its own octonion representation, like the one I showed you at some stage, in terms of E1, E2. So, but these are invariant representations. So similarly, the 1 by 3 charged 3 quarks will have their own Jordan matrix. And so I have 4 Jordan matrices. It turns out color is irrelevant for constructing these Jordan matrices. What are they? They tell us how these 3 generations transform. Electricity has come, I think. How these 3 generations transform under the algebra automorphism which form the group F4. So now getting there, I am interested in eigenvalues. Okay, I can always find these are Hermitian matrices. They'll have real eigenvalues. And the expectation is that since the G2 and the U1 operator already have told me the electric charge is quantized, and how do the 3 generations differ from each other, the 3 particles? In their mass. So the expectation is that these eigenvalues hopefully will tell us something about mass ratios. That's what I was looking for. But turned out they are telling more. They help me fix the fine structure constant. So how to find the eigenvalues of these Jordan matrices? This is their characteristic equation. It's a cubic equation. The same equation is satisfied by X and its eigenvalue lambda. We know that. There are 3 invariant quantities entering here. Trace of X is I1 plus I2 plus I3. Determinant of X given by this formula. If you know the entries, if you know the numerical entries for x1, x2, x3, and if you know what xi1, xi2, xi3 are, you can calculate the determinant. And there's an invariant 2 form which can be made again from a S of x that comes here. So these three coefficients trace the form S, and the determinant fix in an invariant way what these eigenvalues are. So what is going to come out is definitely an invariant, and in that sense looks very important. And let's find out what are these Jordan eigenvalues. So I have a Jordan matrix for neutrinos. Again, it can be argued that the diagonal entries are the electric charge 0, 0, 0. This I think is down, strange, and bottom, if I get my names right. One third, one third, one third. And we can work out from the octonion theory. I gave you an example what these various entries. So this might be something like E1 plus I E2. This might be something like E3 plus, but I make the real counterpart of that because these can't be complex octonions. So all said and done, I'm ready with my Jordan matrices for these four set of objects. I solve the cubic characteristic equation after putting in these octonionic representations. And this is what comes out. I was very thrilled to see that. Just look at these roots of that cubic equation. They are very nice and simple numbers, magic numbers, I sometimes think. This number is the magnitude of the octonion that describes the three neutrinos. That's 3 by 4. For the 1 by 3 quarks, it's 3 by 8. 2 by 3 quarks, it's again 3 by 8. For the charged lepton, the magnitude is 3 by 32. These are the three roots in each case. The central root is the electric charge. Okay, 0, 1/3, 2/3. The other two roots are symmetrically placed around the middle root, minus root 3 by 2, root 3 by 2, and this. It's a conjecture that all the fundamental physical constants of the standard model should come from the ratios of these eigenvalues in some form. This is just a conjecture. I just have some evidence for that in terms of some of the quark Marx ratios, but it remains to be proved. But this is enough information to yield the low energy value of the fine structure constant. The other beauty is, this everything, these are all numbers in base 4, because this 2 cube. So all of these can be written using 0, 1, 2, 3, their powers, and the square root operation. I think one day I hope somebody will find a deeper meaning of these numbers. If charge is important, and if charge is appearing in this set, how can these other numbers not be important and just be, something artificial? Okay, so now two numbers to remember. The magnitude of the octonion for the charged leptons, 3 by 32. This will be used. And the Jordan eigenvalue for the anti-down quark. Why do I use this? Because this is the smallest charge. The smallest charge, lightest particle. This will be used to fix the constant alpha in our theory. Okay, now this is the fine structure constant slide. Alpha square LP4 by L4. This is what comes out as the coupling in front of the charged lepton. This I already showed you. H cross and C are already there in our theory once H cross has emerged. So these are, just scaling. This is square of the electric charge must be this, because this is the coupling in front of the electromagnetic term. How do I fix LP by L4? That's straightforward. That was the magnitude of the octonion for the charged leptons. That was 3 by 32. So 3 by 32 squared is 9 by 1024. How do I fix alpha? I made an assumption that if alpha was to vary with charge, how would it vary? I made this assumption. This needs better proof, I think, but looks plausible, that alpha varies logarithmically with q. That is this relation. And I freeze alpha. Alpha should have a value for my theory. I freeze it by saying that the proportionality constant is the Jordan eigenvalue for the anti-down quark, that is this number, and QAD is the charge of the anti-down quark 1/3. So now we are ready. If I freeze alpha like this, I get alpha squared that goes in here, and LP 4 by L4 is 9 by 1024. We are home now. You can check on your laptop or on your phone. This is the number. it matches with the measured value of the fine structure constant to the sixth decimal place. In the seventh place, here is it 0.07297 Here it is 1, and here it is 3. So the 2 parts in 10 to the 7 is the difference. And in the paper, I argue that should be a certain so-called Caroliazzi correction coming to this number, because we measure this in this sort of 4 dimensions. We in an 8-dimensional space, there'll be a small correction. And you can show that if you assume the electroweak energy breaking scale to be, say, somewhere between 1000 and 100 GeV. It turns out at that 144 GeV, you can match this number exactly to the measured value. And if you choose something like 156 GeV or 230 GeV, you will get more accurate than this, but not this exact, this core data 2018. If you insist on reproducing this, you can do this at a certain electroweak scale. It still remains to ask whether the discrepancy, could it be because the fine structure constant is changing a little bit with time? This is the primordial value. I don't know. In this theory, there is no scope, no cosmology I've done which could tell me that the fine structure constant is evolving. I would much rather believe in the Caroliazzi correction and say that the theory yields the E square by h cross c quite well. I must say that I'm quite thrilled by it. You should look at it critically. If you think I've missed something, please let me know. Otherwise, this is, I think, a nice formula. Again, everything in terms of 2, 3, powers of 2 and 3, and the exponential function, and the square root of the square root, the exponential, 2 and 3 and 1. And that's it. I'm done. I think I will, if you can check this later on the recording in YouTube Live, some predictions of the theory at low energy, some falsifiable predictions, what remains to be done. And this is my favorite fine structure constant quote from Pauli. Just look at the second line. To reach the one, to understand where the 1 by 137 comes from, we shall presumably have to pay with further revolutionary changes of the fundamental concepts of physics, with a still further digression from the concepts of the classical theories. Look at the vision. It's 100 years ago. He's saying this, and only now people are finding that, deal with 8-dimensional octonionic spaces, a pre-space-time, pre-quantum theory, trace dynamics, non-commutative geometry, Jordan algebra. You do all that, and you get a 1 by 137. But he could see that the answer is not going to come easily. You cannot get this answer staying in the framework of quantum field theory and general relativity. We definitely have to go beyond. The last thing I should mention is that 8D octonionic field theories are shown equivalent to supersymmetric field theories and string field theory in 10 dimensions. So whenever you have an octonionic dimension, you add 2 to it. Quaternionic 4 is 6-dimensional Minkowski spacetime. Octonionic 8 is equivalent to 10-dimensional Minkowski spacetime. So one must definitely try to go back to see when string theorists were studying octonions, what did they do differently that they did not see this? I do not have an answer for it. I hope some string theorists will delve into it. And I think we are, in a sense, back to the octonionic dynamics. It probably has a lot to tell us, especially if we go back, extend this to the group E6 beyond E4, then it makes contact with what are known as left-right symmetric extensions of the standard model, the SU2 cross U1 cross SU3 cross SU2. There's SU2 left cross SU right, SU2 right. That SU2 right is very much like what I have for the Lorentz symmetry. So it looks like that above this electroweak symmetry breaking scale, we should look carefully at the left-right symmetric extension of the standard model. They are known to have very good phenomenology. There is a dark matter candidate. There's an explanation for the strong CP problem. There is an explanation for matter antimatter asymmetry, and a precise matching of the 3-gauge coupling. This I just read in the literature that E6 and its phenomenology using this extended standard model is very promising, and that seems to come out from here also. If the fine structure constant is coming out, and if we have these Jordan eigenvalues, we must understand, try to find out if they have something to do with mass ratios, and more generally, what do they mean? Are these numbers, are these numbers don't look, arbitrary to me? They are, if the charge is telling us something, I'm sure the other numbers are also telling us something. So on this encouraging note, I will stop. Thank you so much for listening to me, and my apologies for this, electricity breakdown. So
That's
I'm
okay.
done.
That's okay, DP. That's okay. So thank you, DP. I'll just like to thank DP again for this very interesting talk. As a colloquium coordinator, I found it hard to follow because there are some things that are so deep that as a chemist, I will not be able to appreciate. Maybe there are other people in the audience, and I'm sure Unni has some questions. And yeah,
Yeah,
Unni.
Uni, please go ahead.
Since time is limited, I will focus on this fine structure constant.
Yeah.
Okay. See, whenever here, of course, the matching is impressive. Therefore, that is why what you think as one of the highlights of this. In fact, it looks like magic, because instead of just saying, putting together some numbers from number theory or any other mathematics, here you are also adding a physical reason for the fine structure constant. So there is a difference. And if that matching is not just a coincidence, it's very impressive. But whenever you see such a magic, there's some certain sleight of hand or a sleight of mind. And
On the part of the author.
I notice one such sleight of mind here.
Yeah.
I want to just point out that.
Please. Yes.
So you have taken yes, it's the right page. So you have this 9 by 1024 as the LP square, LP by L to the 4. That's fine. But alpha square, for that you have decided to use a quark instead of the lepton.
Yes.
Which is an aberration according to me, because see, let me just complete.
Yeah.
See, the fact that Sommerfeld talked about 1 by 137 was related to the fact that he was doing atomic physics. So the electron was a charge he was considering, E square by h cross c. Therefore, is 1 by 137 for him.
Yeah.
But if he started with the quarks as a basic units of electric charge, the fine structure constant would have been 9 times smaller.
Yes.
Here you have mixed up the one.
I'll tell you why I have done.
I don't find that logically consistent.
No, I think I will put the logic in. We'll go back to the Lagrangian. So that part is not a problem. Let's see where the Lagrangian is. Yes, look at this Lagrangian. First thing is that in this theory, electromagnetism is a derivative of QCD. The SU3, or rather the U3 symmetry, which is SU3 cross U1, there are generators coming from that so-called Clifford algebra. The U1 number operator is actually made from the generators, SU3 generators. That's why you see it's alpha square. What is important to note is that this alpha is also coming in the QCD coupling constant. The LP square here, I'll take the job from the octonionic magnitude for the 1/3 quark. If I put it in here, I actually get a decent value for the QCD coupling constant, not badly off, quite nicely matching with the data. So
I could have taken the alpha square from any of those, right? Why did you?
No, I must take alpha is more fundamental than alpha square.
But that doesn't mean that you have to take it for the smallest charge.
that is an assumption. Yes,
That's what I'm saying.
That's an assumption that I must take the Jordan eigenvalue for the 1/3 chart. That is an assumption. I will try to prove it from the Lagrangian. Right now, I don't have a proof.
And another thing is the matching to the 7 decimal place is also the problem here, because it is very well measured.
Yes.
So the difference between what is measured in the low energy limit and what you have a prediction for, the difference is 1,000 times the error.
Yeah. No, but as I said,
it's a serious problem according to me.
If you please see my paper, I explain why the theory must provide a so-called, quantum gravitational Carolyasi correction, which I did not invent for this. The holographic theories always have
an uncertainty principle kind of a correction.
Yes, no, but RMS correction.
There it will be plus or minus. It cannot be in one direction.
It's RMS. It is RMS. It's a mean value.
Yeah, so it can be plus or minus. Uncertainty correction, no?
No, but
you cannot take it in the right.
Your fluctuations.
Yeah, therefore the mean will not.
Why did I add it and not subtract it? It's like,
No, you cannot do that.
X square plus delta X square kind of thing, you see. It's like adding in quadrature, I mean.
Okay.
Okay.
Well, I think we will continue. We can have this discussion, but I'll let Amol ask a question. Amol has been raising his hand. Amol.
Yeah. So I don't claim to have followed everything. So I have only a couple of bits and pieces question.
Go ahead.
So one is about see, with this Jordan matrices, you got the charges of the objects to be 0, 1/3, 2/3, and 1.
Yeah. Actually, the charges already come from the previous discussion. Yeah. There's a reason why this reproduces that.
Yeah. So of course, you mentioned that 1/3 corresponds to anti-down quarks and 1/3 corresponds to up quark, of course. Now, anti-down and up actually transform quite differently under SU3, no?
Triplets and anti-triplets.
So is that a problem, or is only the magnitude of this relevant?
No, that is not a problem. Only the magnitude will be used. And in fact, I didn't use up quarks. No? I used only the anti-down. For the fine structure constant calculation, I didn't use these magnitudes at all.
Yeah. So this is not about calculation. This was about just a nice nice pattern that you got by getting these 4 as values. It would have been great if it was 1/3, because then the SU3 group would have come out nicely out of this.
Which one should have been 1/3?
No, instead of 1/3, if you had minus 1/3, for example, then because then both of these will transform similarly under SU3.
No, Amol, what is happening? I understand. What is happening in that Clifford algebra representation of the quarks and leptons? The following set comes together. Basically, all the positively charged things come together. So the neutrino, the positron, the anti-down quarks, which transforms anti-triplets, and the up quarks, they come in one set. And then you make a conjugate of that and you get the antiparticle. It's a very good point. You are saying, why didn't the down quarks come in the same set as the up quarks? That's what you're saying, no?
Yeah, because they are the same. They transform similarly under
SU3. That's a very good point. I don't know the answer to that.
Okay,
that is how it emerged from the algebra. But I will try to think about it. I somehow thought it's okay, but you have a good point. Yes. This is actually not this part is Cold Fury's work. It goes back all the way to Gunedin and Gussi, 1976. The first persons to suggest that the octonion algebra can yield this quark charge quantization and quark transformation property. So this has been around for a long time.
So we're going to ask one more quick question.
Yeah.
So this goes back to the earlier part of your talk, in which you introduce spin by having this rotation between 4 space-time plus 4 extra degrees of freedom. But of course, you still have the Lorentz group, right? And Lorentz group, if I understand correctly, would still also give you our normal spin.
Yes, a very good point.
So what happens to normal spin in this framework?
Yes. So to some extent, I worked to show that the spin that we normally define from the Lorentz group match this. but I need to do more work. What precisely needs to be done is the following. What I have here is a SU2 cross SU2, from which, one of the SU2s I can complexify and get the SL2C. But I have to try to define spin using this entire structure. You see what I'm saying?
Okay, now I'm trying to understand.
I don't know
Go
how
ahead, go
to
ahead.
do it. Someone who has more expertise than me should do this. That I should use either the SU2, either the Lorentz algebra part of Lorentz we can define spin, or you should use the whole of it. There should be a proper group theoretic definition of spin in this theory using the algebra. I totally agree. But whether that should be done with SU2 cross SU2 or just some answer, I would like that to be done. I agree.
Sir, excuse me, sir. Sir, can I add a small point here? So this SL2 comma C as the spin cover of Lorentz group. So could you write a complexified version where the spins that you are talking about, the rotations, as a complexified group where the real part takes the SL2 comma C?
Yeah, I think that's related to what Amol is asking. I would like to do it. I haven't gotten down to it. I'm right now after the mass ratios because I'm hopeful they will come out of these eigenvalues. And also I have to relate this to the Lagrangian dynamics to understand these Jordan eigenvalues better. But yes, what you said should be done. It just looks doable, but I have not gotten down to it.
Okay. Okay, so I guess it's been an extended session. So I thank all of you, and especially TP for this very I think enriching talk. I'm sure people will go back into the YouTube again and listen to it with a greater detail and patience. But thank you for illuminating us. And I hope if there are questions, more questions to TP, please use the chat box on the YouTube. That would be helpful. And that's why we have put it in the TIFR Platinum Jubilee channel. So people can actually visit and
the recording stays there, is it?
Yeah, the recording stays there. Absolutely.
Okay.
So unless you want to take it off, so TP.
No, let it be. Except for the electricity disruption, I don't know how that will show up there.
No, that was fine. It's okay. Don't worry about that. And so I guess that's what we conclude. We would like to thank everyone in the audience as well for being here, and also people in the AG66 lecture theater, especially Rajesh Mistry and his crew, for being there and keeping this entire show running over in the lecture theater. On some popular demand, I think we will start the tea and snack at some point of time at the end of this month. So please, I'll keep you posted on that. But it's not happening today, unfortunately. But we will try to do that. And yes,
some people in the lecture theater, is it?
There are some people in the lecture theater who attend.
Okay. That's good. That's good. Yes.
And just to conclude the session, I would like to invite you again for the next week's colloquium, which is going to be given by Professor Vivek Polshettiwar, who is my colleague in the Department of Chemical Sciences, and he is going to talk about essentially sustainability of life on the planet, as well as magnesium civilization in Mars and use of nanotechnology to address some of these problems. So I thank all of you for being here, and I thank Dr. Satyanarayana for helping me with the YouTube live link.
Okay, thank you everyone. Bye-bye.
Thank you, TP.